All right, this is part two of a video in which we aim to show this theorem that I have for you in blue, where if G is a region in the complex plane, remember region means an open connected subset of the complex plane, and if you've got a function f whose domain is G and it spits out a complex number, and if that function f is such that the derivative f prime of z is equal to 0 for all inputs in that domain G, then you can conclude that f is a constant function on G. So if you haven't caught part one, that's where we talked about the analogous result from Calculus 1 that you might remember that utilized the mean value theorem. Now, in a complex analysis class, we haven't gotten to anything like a mean value theorem for complex valued functions. And so what we're going to do instead is a little bit more of an intrinsic approach that utilizes the topology of the complex plane that's really introduced by the absolute value. So let's get into some of that topology, and then this video will culminate with the proof of this theorem in blue. But we're going to set up a lot of the topology definitions and results that we need to do that proof. So let's start off with our first definition here. We're going to say a subset of the complex plane G is connected if there do not exist non-empty open sets U and V of the complex plane such that U union V gives you back G, and U intersect V gives you the empty set. So in other words, a set G is connected if it's not possible to split it into two open sets that are disjoint from each other and whose union gives you back the set G you're interested in. So you can't split it into two non-empty disjoint open sets. All right, so let's look at our first lemma. So if G is a region in the complex plane, and remember region is a vocab word, that is an open connected set. So if you've got an open connected set in the complex plane, then for any two complex numbers in that region G, there exists a path, I'll call it gamma, from Z to W that's contained in G. Remember, a path is a continuous function whose domain is the interval from 0 to 1, and it spits out complex numbers, and it's a way to connect these 2 points together. And what you might recognize this result as, this lemma 2, it's really a specific instance of a more general result about open subsets in Rn. Remember, you can think about the complex plane with like the topology or the metric introduced by the absolute value. It's really the same thing as R2 with the Euclidean metric, right? The distance function you know from college algebra, right? So they behave the same way topologically. And so what we're really saying in lemma 2 here is this, maybe more general result, or depending on what classes you've had if you're watching this video, more familiar result, that open connected subsets of Rn are path connected. So path connected and connected are equivalent in that domain when you have an open connected subset. Okay, so what's the proof of this look like? And it's a fun proof. So let's let Z be an element of our region G. And we're going to look at two sets. The first set I'll call capital P, and that's all complex numbers W from G, such that there exists a path from W to Z. So like Z is this fixed thing I'm going to refer to all the time, and now I'm saying let's consider all the points that can be connected to Z by a path that's contained inside of G. And let's let P prime be the complex numbers in G such that there's no path that connects W to Z. And so just to give you a picture, what I'm trying to do is I'm trying to take G and I'm trying to split it into two pieces. One piece consists of points that can be connected to Z via some path, and the other piece in blue consists of the points that I'm saying could not be connected to Z by some path. And so what we notice then is that, they don't have any overlap. That's really the second criteria. Their intersection is empty, and then their union should give you back the whole set G, right? So if you're a point in G, either you can be connected to Z by a path or you can't. So P union P prime is G. And so what we're going to try to show is P prime is empty, which forces P to be the whole set G, which says that every point in G can be connected to Z. So since Z is arbitrary, take that to mean every point can be connected to each other. So that's the big picture. That's the bird's eye view of what this proof's going to be. And so the way that we've set this up too is we're going to try to do this. We're going to try to show that P prime is empty, therefore P is equal to G. And the way we're going to do that is we're going to try to show that both P and P prime are open sets, because then we could utilize, if I scroll back up, the definition of being connected. So by definition, if it's connected, there should not exist two open, non-empty open sets that split G into two pieces and union to give you back all of G. Okay, so that's again the big picture what we're going to try to do. So let's do it to it. So first, as I got in my picture, let's let X be an element of P. And so by hypothesis, I don't know why I put P and G there. Sorry, I should have said X and G, not P. Since X is an element of G and G is a region, it's open. So that means that we should be able to fit some little disk around X and fit it inside of G. So there should exist some radius R for which I can put that disk centered at X of radius R inside of G. So remember, that's the D bracket X comma R notation. That's just my kind of open ball notation. And so just in a picture here, I've introduced a y in the picture. I'll talk about y in a moment. But so far I'm saying, look, X is the center of some ball that fits inside of the domain G. Now what I need to try to do in my picture here is, why is it the case that that ball, how do I know it's completely contained in the red? A priori, I don't know that yet, and that's what I'm trying to prove. So just the way that I've drawn it, don't take that for granted. What I'm going to try to show you is that it's possible to do that so that, yes, it does fit inside the red. Okay, so for any other point, so now I've got any other point y that is inside of the disk here. And remember, like in my picture, it looks like y is already in P, but I'm just saying, look, take y to be any other point in the disk. So I'm not guaranteed right now that it's in P. It could be in P prime. I'm going to show you it's not in P prime though. So anyway, so for any other point y that is in the disk, I know that a straight line should connect x to y and should stay inside the disk. And so the straight line, the way I'll write that path down is with this gamma here. So x times 1 minus t plus y times t. And I know that that straight line from x to y, again, should be contained inside the disk there. Okay. And so I've drawn you a little picture over to the side just to try to convince you that, yes, that line segment is contained inside the disk. Okay, so, well, x is an element of P. And then what is P again? So capital P is, well, x is a point that connects to Z somehow by a path. And so I should be able to obtain a path, I'll call it gamma tilde from x to z. And what should we do now? Let's just take the union or the concatenation, whatever you want to say, of gamma with gamma tilde. That would be a path that connects y to x and then x to z. Therefore, that's a path that connects y to z. And so there's a picture there about what I'm trying to get at. So I've got a path, I've got a way to get from any point inside that ball centered at x over to z. And so what that shows me then is that, well, y itself is an element of P then. So since y, there should be a y there, I'm not sure where it went. Since y in that disk was arbitrary, that tells me that that disk had to be contained inside of P. So again, that is how I would justify how I know that that disk actually has to be in the red. It cannot slip into the blue at all or outside of it at all. And what we just showed is that any point in P has a neighborhood that's contained inside of P, and that's a quick way to say that P is open. So now let's try to play the same game and try to show that the blue set is actually open as well. So let's let x be in P prime now. So again, because x is in G and G is a region, I know that it's open, therefore it should have a neighborhood that's contained inside of G. So I'll call that, again, dxr, say. So the disk centered at x of radius r. And let's consider that now. And let's let y be somebody else that's in that disk. And we're going to try to play the same game here. So we're going to try to convince ourselves that y is also in P prime. Just like a moment ago, we convinced ourselves that when x is in P, and if y is in that disk, then y is in P. We're playing the same game now. If x is in P prime, I take this little disk centered at x, then any point inside that disk is going to be inside P prime also. So we're going to look at the same thing. I know I can connect x and y with a straight line because we still live inside the disk. It's the exact same picture as I've got up here on the right-hand side, connecting x and y. Now, if there existed a gamma tilde that connected y to z, then the union of gamma with gamma tilde would connect x to z. But x lives in P prime, and there is no path that connects x to z. Right? That's the criteria. That's how we defined P prime. So that tells me that there cannot be a way to get from y to z. And so in my picture there, again, I do not have a way to get from y to z, because if I did, then I'd have a way to get from x to z, but that contradicts that x is in P prime. Therefore, no path connects y to z, and another way to say that is that y is an element of P prime. Right? That's the criteria to get into P prime. There's no path that connects you to z. So y is in P prime, therefore what we've shown then is that any point inside that disk is in P prime, so therefore the disk is a subset of P prime, and of course what we've also just shown is that any element of P prime has a neighborhood that's contained in P prime. In other words, P prime is open. Now, We've done it. We've shown that both P and P prime are connected. And let me remind you too, I'm sorry, not that they're connected, that they're open. And let me remind you too that P and P prime were defined so that their union is G and so that their intersection is empty. And now, since they are two open sets and G is connected, they can't both be non-empty, right? That would contradict that G is connected. So it must be the case that at least one of them is empty. So one of them has to be empty. Now, what do I know? Well, I know that Z, connects to itself by the trivial path. So P has stuff in it, right? It's at least got Z in it. So P can't be the one that's empty. Therefore, it has to be P prime. So since Z is in P, we must have that P prime is empty. And now when I think about, say, the fact that P union P prime gives you back G, well, if P prime was empty, that just says P union the empty set is G. So of course that says P is equal to G. So that tells me P is G. And again, therefore, that tells me that any 2 points in G can be connected to each other by a path. Fantastic. So that's the end of the proof of lemma 2. Let's move on to another result that we'll need. So lemma 3 is any 2 points that are in an open disk can be connected by a chain of horizontal and vertical line segments that are contained inside the disk. And we'll look at a picture too to go along with this proof. So let's let DZR just be an open disk. So the center is Z and the radius is some positive real number R. And let's take 2 points X and Y that are inside this disk here. And let's consider the line segment that, it's horizontal and it cuts through the middle. And the way I'll write that down is it's like A plus I times the imaginary part of Z, where A gets to run from the real part of Z minus R over to the real part of Z plus R. And if that's a little bit confusing, just in a picture here, I'm just talking about this horizontal line segment, right? The farthest left it goes is whatever the real part of Z is minus R, and the farthest right it goes is whatever the real part of Z is plus R. And then notice the imaginary, the imaginary part of Z is fixed, right? So like there's no vertical shifts in that segment at all. It's flat. Okay, so what we're going to do now, and so I picked X and Y just be any 2 points that are in the disk as well. And remember, my goal is to just in some way try to create some horizontal and vertical line segments that can connect me from X to Y. So there's no one way to do this. Let me just tell you about the way that I thought of to do it. Let's define the point X tilde, and let's say that's the projection of X onto L. And so namely, X tilde is going to be the complex number whose real part is just the real part of X. And whose imaginary part is the imaginary part of Z. And similarly, we're going to define the complex number Y tilde, whose projection, that is the projection of Y onto L. So in other words, Y tilde is the complex number whose real part is the same as the real part of Y, and whose imaginary part is the same as the imaginary part of Z. And if you're a little bit confused about what in the heck am I doing, I've got a picture. I'm just saying if you've got X, just drop it down to that horizontal line L, and that's X prime, that's X tilde. So that's what I mean by the projection. And if you've got Y, just drop it down to the horizontal, and that's Y tilde. And now what I want to think about, or just what I want to notice, is again, what am I after? Do I have a way to use, really finitely many horizontal and vertical line segments to get from X to Y? And in my next picture, I show you one such way to do that. I'll start at X, I'll go down to X tilde, I'll go over to Z, over to Y tilde, and then down to Y. And the union of those, 1, 2, 3, 4 pink paths is a perfectly good path that is what I'm after. And I thought a little bit with some linear algebra to try to describe that as a path. And so maybe you could try to do that for fun. Just remember a path, its domain is the real interval from 0 to 1. That's why I'm being a little bit funny with my piecewise from 0 to 1/4, from 1/4 to 1/2, etc. until I get from 3/4 to 1. But again, how do I get those formulas? It's just a fun little exercise in linear algebra that I encourage you to try to do. But there is a concrete formula for the path that's pictured over there to the left. And so what's the point is that path is completely contained inside the disk, and it only consists of vertical and horizontal line segments. All right, so we're flying through these lemmas. Lemma 4. Lemma 4 is if G is a region in the complex plane, then any X and Y can be connected by a chain of horizontal and vertical line segments in G. So this is pretty similar to lemma 3. I'm just saying life is good inside of a disk, an open disk, you could do that. And I'm saying you could do the same thing inside of any region. And what we're really going to do is use lemma 3 in order to prove this one. So we're just kind of generalizing lemma 3 a little bit to, any open connected set. In some ways, a disk is like your favorite open connected set. It's easiest to work with. All right, so by lemma 2, I know that there exists a path gamma, remember whose domain is 0, 1 to g from x to y. And I've introduced x to y to you. Those are my two arbitrary points in the region G. And so that means that gamma of 0 should be x, that's where you start, and gamma of 1, that should be y, that's where you end. And what we're going to do is we're going to take the interval from 0 to 1, so the domain of gamma, and we're going to partition it. And I'm saying t0 is 0, and I'm just going to chop it into a bunch of pieces, and tn will be 1. That's the last point. What we're also going to do is we're going to choose, for each one of those partition points, I'm going to choose a radius called ri. It's bigger than 0. And I'm going to try to choose it so that the intersection of two consecutive open balls centered at partition points is not empty. So like two consecutive open balls that are centered at my partition points, they have to have some overlap. And the other thing I'm going to try to do is to choose these things so that, of course, these balls should all be completely contained inside of G. And you should convince yourself that we should be able to do this, right? G is open, so that I know that every single point has a ball that's contained inside of G. And what I'm saying to do is, if need be, I'll just throw more partition points in to guarantee that when I take the ball at each partition point that they have some overlap. So I'm able to throw more partition points in as needed to make the radius smaller if needed, all that good stuff. So convince yourself that you can do that. And I've just got a little picture for you right here, right? There's my set G, and I'm just saying I'm going to partition the path from x to y in such a way that these neighborhoods have some overlap as I go. Now, why do I care about that? Because when I have some overlap there, I'm saying that there exists somebody zi that's in the overlap of two consecutive open balls here. And I've got another picture for you in a moment. But by lemma 3, that tells me that lemma 3 told me that I could connect points inside of my open ball with chains of horizontal and vertical line segments. So I could connect those. And so, well, if I'm allowed, if I know that two open balls have some overlap, why don't I just connect the vertical and horizontal line segments to the guy that's in that overlap? And here's where my other picture is. So what I'm saying, if I zoom in a little bit, I'm looking at the ball centered at gamma T2 and at gamma T3, those two balls. If Z3 is in their overlap, right? Well, I know gamma T2 can be connected to Z3 with like a horizontal and vertical segment, but then I know Z3 can connect down to gamma T3 with horizontal and vertical segments. And all I'm saying is, you just connected gamma T2 and gamma T3 with horizontal and vertical segments. So that's what having some points in the overlap buys us, that we can connect these all the way down from X all the way down to Y with just some horizontal and vertical segments. And so that, of course, finishes the proof of that lemma. So we're finally got enough topology in order to prove the theorem. And you've probably forgotten, like, what is the theorem? This guy's been going on and on about topology. What are we after here? So remember this theorem. If G is a region in the complex plane, remember that's open connected set. If f's a function whose derivative is 0 for every point inside of G, then that's enough to conclude that f is constant on G. So let's look at the proof of this. So let's let z be a complex number x plus iy, and I'm introducing that so that it makes sense for me to talk about the real and imaginary parts of the function f. So f has real part u of xy and has imaginary part v of xy. And remember, u and v, those are real valued functions, right? You plug in x and y to those and it spits out a real number. Let's let h be any horizontal segment that lives inside of G. And so if it's a horizontal segment, remember that means that there's no change in the y coordinates for anybody on that segment. So that means there exists a specific y0 that's fixed, a specific real number y0, such that if z is an element on that horizontal segment, then I know what it looks like. It looks like x plus I y0. And again, I'm just trying to emphasize the imaginary part is always y0, and x is the only thing that can change if you're on a horizontal segment. So that allows us to consider u and v not as functions of two variables, x and y. If y0 is constant, then u and v are really just functions of x whenever I think about only plugging in points on this horizontal segment h. So u and v are real valued single variable functions because y0 doesn't change. So in other words, again, just to restate that, I'm restricting f to only plug in points on h, but then that restricts the components u and v to only plug in points in some interval from a to b. So for some real numbers a and b and r. Now by hypothesis, remember we have assumed that f prime of z is 0 for all z in G. Well, if h is in G, then f prime of z is 0 for all z in H as well. And remember, f prime of 0, its formula is the partial of u with respect to x plus I times the partial of v with respect to x. And so let's substitute all this good stuff in. That says that 0 plus 0i is equal to the sum of those partial derivatives, or those components. And remember, two complex numbers are the same if only if their real and imaginary parts are the same. So that tells me that the partial of u with respect to x is 0 for all x, and the partial of v with respect to x is 0 for all x inside this interval. And now, what do we know? These two things satisfy lemma 1. And lemma 1 was introduced in part 1 of this little series of videos. Lemma 1 is just the corresponding result from calculus 1, that if you've got a function on an interval whose derivative is 0 for all points in that interval, then the function is constant. So what we're saying here is that u and v satisfy that, right? They are good old calculus 1 functions when I restrict to a horizontal or a vertical line segment. So we can conclude that u and v are each their own constant. I'm not saying u and v are the same constant, but I'm saying u is constant on this interval and v is some other constant on this interval as well. And so that tells me that f is constant, right? F looks like a plus bi, where a and b are fixed is all I'm trying to say. Now a similar argument would show that f's constant on any vertical segment that's contained in G. And if you took 2 points now, z and w, that were in G, lemma 3 told me that I can find a chain of horizontal and vertical line segments that connect z to w. Now I know that f's continuous, and I know that f is constant on each of those vertical and horizontal line segments. So maybe you're worried, well, how do I know it's not a different constant on each segment? How do I know that? Well, this is where, again, f being differentiable implies it's continuous, and continuous helps us out here. Because it's continuous, that means that the function has to have the same constant value along each of these line segments. So that tells me f of z has to be f of w. And I've just got a little picture there for you as well there. I know because f's continuous there, when I zoom in, when I take some arbitrarily small little disk around, say, that point in the corner over there, I know that the values of f of z and f of w, right, they have to be like, within epsilon of each other. So that means that they eventually, I guess we're trying to say that they have to be the same. Have to be. So what have we shown? We've shown that any 2 points from G, they yield the same output. And of course, that's the same thing as saying that f is constant on G.